Good afternoon, everybody. I'm Ananth, and I'm a senior architect at CBA. I'm a contributor to Apache Apex, and my contributions have been primarily with the Cassandra connectors for Apex and also the Kudu connectors. Recently, I've been putting together the Python connector, and in this context, I'd like to share some design patterns which can be implemented for model scoring on these data processing platforms using Apex as the engine for low latency scoring. Basically, what I'll try to quickly summarize what others have spoken today, as well as what Bob spoke yesterday. We are quickly in the world, landing in the world of using machine learning more or less for many as a solution for many business problems, and this requires both the engineering community to come together and the data scientist community to come together and build a real world application. Now, the problem with this approach is that, the problem with the current stack technologies is that you don't always get all the requirements in a single framework today. There are various process related issues and a whole lot of other things which don't act well together. And for example, if you take the machine learning stacks which are available today, they are not really geared for low latency as the primary construct. They are more about modeling or scoring the model, and as opposed to the other data processing pipelines, which basically will solve some bits and pieces of it. Primarily, this becomes more complicated if it is a streaming solution kind of thing, wherein you want to take the same model which is being developed, for example, in R or Python, and convert it into the scoring component in a JVM world. Right. So, as part of today's agenda, I will be covering Apache Apex, introducing Apache Apex to this forum. I will also be covering a few bit of data processing patterns and also some model scoring patterns which we can build using Apex. Apex is primarily defined, can be defined as a low latency distributed streaming engine. Basically, it has got some other highly appealing features, like it's a customized, it allows a highly customizable DAG, it provides checkpointing, end-to-end exactly on semantics, security, and it's YARN enabled out of the box. I'll walk through the various facets of Apex by a few use cases here. First is what do we mean by a low latency streaming engine? I think the primary differentiator is that you are looking at a tuple based processing as opposed to a mini batch based processing paradigm, in the sense that in the lower section of the processing model, you are actually optimizing for throughput. Typically, Sparks kind of thing are really good at doing this. They really do it really well. Whereas that streaming frameworks tend to look at a tuple at a point of view. That means they are optimizing for latencies as opposed to throughputs. Right? That is the primary differentiator. And this kind of engines make sense when you are looking at some use cases like fraud prevention. Kind of use cases wherein the processing sits in between the transaction and the human experience, as opposed to fraud detection which happens post the transaction. Once we choose the engine we want to build our stack on, the next problem would be I want to turn it into a distributed kind of thing as well, because one single node might not be able to meet all your compute needs, right? And so Apex is just like other streaming engines, does provide a YARN enabled compute model, wherein your containers are scaled up and down, or scale up and scale out kind of paradigms. That means a single node can do a scale up problems, and a multi node cluster can do a scale out paradigm as well. There's no MISO support yet for Apex, and it's still on the roadmap. This slide talks about the typical application layout of Apex, which is basically Apex is nothing but a collection of containers, YARN containers, and what we have is an application master which is highly available, and the compute nodes which do the business processing logic, and they are distributed across your cluster. They sit on your typical Hadoops, and you can co-share this cluster with your Spark jobs or typical MapReduce jobs, and have a streaming engine which will meet your latency needs. And each of this is aware of failures, in the sense that a master can fail, and Apex master can be reprovisioned on another physical node if the physical node fails, and those use cases are also managed. On the left, you will see the typical layout of the Apex application framework, wherein at the lowermost you have the bare metal or the cloud or virtual, whatever your mechanism is to provision the OS, and on top of it you have your Hadoop nodes, the data processing nodes, and on top of the Hadoop yarn constructs you have the Apex streaming engine, which provides high performance, fault tolerant and in-memory processing semantics, and on top of Apex you build your application to get all these benefits. This is a typical example of an Apex application development model, wherein you basically first try to build the logical model of your application. In this example, we are streaming something from Kafka. It can be a TCP socket as well, whatever our choice is, and then we are using the tuple which is read out from a Kafka partition, and look at, say for example, Cassandra store to enrich the transaction, to define a feature or maybe a collection of features, and use this feature and perhaps run it through a model which scores the transaction in some way, and then perhaps write it to another store like Kudu, which will help me put a relational engine on top of Kudu so that I can query like an SQL query kind of things. This is the basic simple example. So in this example, what we see is the arrows there which represent the stream of tuples going in from one version of the operator to the next stage. It's a flow going from left to right. The circles you see can be defined as operators. This is nothing but a JVM instance which holds the business logic specific to your component of the problem you're trying to solve in that piece. So in the first piece you have the business logic of it's not business logic, but at least the data problem of reading from Kafka, scaling it to perhaps multiple partitions and topics or clusters or whatever it is. And then the second stage you have the problem of reading from Cassandra. It is its own operator, the model is the third operator, and so on and so forth. All of this in Unigine makes up a DAG wherein it's a directed acyclic graph between left to right as a flow. So the entire thing, which is the collection of the stream and operators, make up the DAG, and that's what make up an Apex application. Apex comes out of the box with a lot of connectors out of the box. It's basically the time to value or time to market is really low because you have so many connectors ready made out of the box, so that you can basically piggyback on that and try to extend it in the way you want it to be. The next problem you might hit is, yes, that's all fine, but when I build my application might itself have different compute needs. For example, reading from Kafka might be pretty latency, low latency, because Kafka is really optimized for a streaming consumption point of view. But for example, if it's a the Cassandra lookup wherein I'm doing multiple keys or multiple tables in Cassandra doing lookup, I might end up with a disk IO access pattern which might be slower as compared to Kafka streaming, and going down the path you might have a model scoring which is highly needing more compute because your scoring function is really rich and you need more compute kind of thing. So Apex provides the ability to configure or fine tune your loads basing on the part of the problem you're trying to say. In this example, you are looking at Kafka has just three operators. Perhaps Cassandra is also not really having so much load, so we still went with 3 operators. But model scoring is really compute intensive, so we went with a deployment of 6 operators, and Kudu was handling perhaps with just 2 operators. What Apex allows is you code for the logical model on the left, which is represented by 4 circles connected the straight DAG there. But while deploying, you can just make it as a configuration aspect to actually turn it into a model which meets your latency needs end to end. Right, and the entire thing is configurable in terms of a stream codec. So, for example, you can fine tune your tuple routing patterns across these operators from each vertical face to other by defining your own stream codec. If you are coming from the world of Storm, basically you will find that there's a lot of similarity in this architectures in that way. Right. The next problem you'll hit when you try to build some of these low latency thing is that, of course, I might have 6 model scoring operators and 3 Cassandra operators or 3 Kafka operators. Because there is an uneven distribution of operators, and most of these, most of this pattern might result in a back pressure on some of these because there's an imbalance of computes in the individual operator level. Apex provides the concept of unifiers, wherein you will see that if there is the problem were to be flipped the other way around. For example, we had 6 Cassandra operators in the lower block of the diagram there, and we had only had 2 model scoring operators. You can actually build unifiers to make sure that it is the back pressure is handled properly as well. Another interesting problem space, I think, for people who have worked in Spark, this might be very well aware, is that you can avoid network shuffles. Wherein, for example, in the scoring pipeline, you might read from a tuple coming from Kafka, TCP socket, Cassandra, model scoring, but you essentially need not, or if the application design does not require a shuffle across the nodes, you can put a parallel partitioning construct wherein you only merge when you want to merge. So you can define your DAG to avoid shuffles all the way till the point you actually need it, and that is a building block in the low latency processing world as well. Another interesting feature which Apex provides for is the concept of dynamic partitioning. For example, if we have this traffic or transactions which we are doing as a fraud as an example, I might realize that during the day the transactions are running into, say, millions of transactions, but at the night there are only 2 million as opposed to 20 million. Apex allows for dynamic partitioning in the sense that the same application, without getting down, can scale up or scale down basing on your configuration. It provides such constructs so that you can scale up and scale down basing on your business logic or any other logic, like so the stats, for example, the number of tuples coming into the Kafka partition were 100 in the previous instance window, and now there are 20. You can actually scale down the framework can automatically scale down. So daytime topology, you will have something like on the left. On the nighttime, you can turn it into something like this if you want, and you can use that additional compute which you gain by doing this dynamic partitioning at night for, say, for example, your other batch jobs. So you're investing in a fixed constant hardware kind of profile, and your streaming needs are changing at night perhaps, and you can use the resources released on a nightly fashion to do the batch, for example, some model development or whatever these batch jobs you can do. Another interesting feature that is provided by Apex is PubSub for recoverability. So machines do fail, and this is a hard reality we have today. But how Apex differs from other streaming engines is that it only fails part of the DAG, not the entire application, if something goes wrong. So it's a powerful construct and differs from some of the streaming engines in the aspect that, if, for example, if you see on the rightmost diagram there, if the part of the operator which is downstream dies, the upstream operator knows how to reprovision or resend those tuples in case of failure to the downstream operator. And this is a building block of Apex, because this is this provides for a couple of things. One is idempotency, in the sense that the upstream operator will make sure that your tuples are resent in the same sequence as they were sent earlier, and this is a very important construct when you build applications, because if you want to do end-to-end exactly once, and if you are dealing with stores like Cassandra which don't have transactional or two-phase commit protocols, what will happen is you end up corrupting your data, and this forms a very important building block which we will cover in a few minutes. It also has the capacity to spill to disk, just like your Sparks, wherein you can configure to spill to disk if the memory is getting filled up. This kind of constructs do exist in Apex as well. So Apex also provides for a checkpointing mechanism, which is at certain time windows, the framework ensures that a checkpoint is created for that state of the operator at that point in time, and this checkpoint is specific to the operator, and each operator might be or traversing it on its own time windows when the checkpoint is happening. The example you see here is the JVM, where the tuples are flowing through it, and each set of tuples are bounded by a time window. That's a streaming window, and this is the processing time. You can also do event times in Apex, but this represents the processing time, and once this tuples reach that time boundary, then end tuple is generated, end tuple marker is injected into the stream, using which there can be operator business logic which you can use to do anything which you want to do at an end window or a begin window kind of constructs. You can also do a checkpointing, in the sense that Apex by default uses the HDFS store for checkpointing. That means you have a highly available store for storing the checkpoint itself. Suppose if the operator dies and the operator is provisioned on some other container, that HDFS checkpoint since it's available via distributed store, you can actually use that checkpointing metadata on the second instance of the operator and continue from the checkpoint state itself. The checkpointing itself has got highly optimized to the operator itself. For example, in case of Kafka, the checkpointing metadata can be like the cluster name, the topic name, and the partition which this operator was reading information from, and the offset. So using these 4 metadata points, I can actually reprovision an operator on some other container or a physical metal and ensure that I can resume from a certain offset of a given topic and a given partition for a given Kafka cluster. Apex provides for very varied patterns in the sense that you can stream from multiple clusters of Kafka to multiple topics within each of these clusters and all in one single application. So for example, you can think of use cases like there are multiple data centers of Kafka, multiple clusters of Kafka and multiple data centers. You want your application to process by consuming from multiple data centers. That kind of patterns is also available here. There are various processing guarantees that Apex provides. One is the at least once guarantee. In this, the downstream operator which is receiving these tuples can be guaranteed that the tuple which is being sent from the upstream is sent at least once. That means there's a possibility of duplicates. That is good for some use cases wherein, for example, say log activity data or something which you not really care about if there's a duplicate for a small sequence of windows or sequence of tuples. The other processing guarantee it can provide is at most once, in the sense you configure, I'm okay to lose some data. For example, say heartbeat monitors coming from some device, and it's okay to lose a few tuples. It doesn't really matter because you're latency aware and what you're losing is for a small time window, say a couple of seconds. Then if that's fine, that's another paradigm you can get as a processing guarantee. The third is also supported, which is exactly once, and I think this is the most powerful because it's very difficult to achieve exactly once end to end and support a whole lot of stores. For example, we have seen Cassandra talk yesterday, right? And Aaron was mentioning about, Cassandra provides only something called as lightweight transactions. In the Sparks, in some of the other worlds, there are caveats and what do we mean by end to end exactly once. And I believe end to end exactly once is difficult to achieve. And even in the Apex world, it's actually a combination of compromises done in a different way. What end to end exactly once is basically happening. For example, this is the logic I implemented for the Cassandra operator or the GOTO operators, wherein when an operator gets resumed after a crash or an application shutdown, what happens is that I'm getting a replay of the tuples. For example, in this case, the operator crashed at the second window at the second tuple, and the operator gets reprovisioned on some other instance. Because of the checkpointing mechanism, tuples in the first window are reprovisioned. That means they are resent into the second instance of the operator, but the operator logic is intelligent enough to detect that it's a duplicate window, hence it will skip those windows. It will not even write to Cassandra or GOTOs. But in the second window, it's really difficult to tell because the operator got a handle only at the begin and end window logic handlers. So what in this case we do is we give a callback as a business function callback which an engineer can implement to really say this tuple is a duplicate that's being processed or not, by looking at an external store or looking at the same Cassandra store and decide it's a duplicate or not. That's how this is being solved in the Apex world, wherein we want to achieve exactly one semantics, and it's difficult to achieve end to end exactly one semantics for systems which don't have a two-phase commit protocol kind of things. I'll move on to the next part of the talk, which is these are what we saw till now is the basic building blocks of Apex, and what we are seeing now is something which will help the data scientists and the engineering community to build applications on top of Apex. Apex comes with a lot of operators, as I was saying. One of it is the R operator. Currently, the Python operator that's currently in progress, which I'm implementing, it's going to come soon in the next release. There's already support for H2O, Samoa, and DL4J, for example. Some of these patterns might be not really used in all use cases. For example, some of our integration is more about streaming machine learning as opposed to building your model on a batch mode and then trying to use that model in the scoring thing. I believe that some of these cases are edge use cases for some of, but nevertheless it's integrated. Here is the typical flow of tuples in the R operator which Apex provides for. What is done inside the R operator is you basically the engineer who is trying to implement the model as developed by, say, the data scientist can actually make sure that a certain R script is loaded as part of the operator. So, when the operator launches into the JVM as a JVM instance, what typically it happens in the R operator is that it reads the script and then creates an R engine within the memory of the JVM. And then what you have is these tuples which are flowing through this JVM operator, they get called back to the R script or R function which is enabled as part of the R operator configuration, and hence you can score your tuples if an R script is your model scoring function. Right. Similar model is being developed for Python, wherein it's got some more interesting features. I think one of the interesting features is the NumPy integration. Basically, what we have is a sequence of tuples flowing to the Python Apex operator JVM, and each of this tuple is to be scored using the Python script. For example, someone developed a model, and the model can be serialized by the data scientist and put into the class path of the Apex application. The Apex application, when it boots up, is taking that serialized version, deserializing it, and then just before deserializing it, creates a Python interpreter within the memory space of the JVM. So, it is basically a mini interpreter within the JVM itself. We are taking this deserialized model from whatever has been done by the data scientist, and basically we are using the same Python code to plug it into the Python interpreter which is within the JVM. And then we assume or we engineer the upstream operator to do the feature engineering. For example, the upstream operator is in our example a Cassandra enrich operator, which is reading from Cassandra and transforming the data which it enriched from Cassandra into a feature definition. It comes back into this Python operator, and this Python operator then takes this feature engineering vector and pushes it as for example, as a NumPy entry. And the interesting feature which is happening here is that both the JVM side of things and the Python interpreter side of things are referring to the same memory structures as NumPy structures. That means we are not wasting time in trying to convert a Java data structure into a NumPy data structure and henceforth and so forth. It's basically an optimized version for low latency as well. I think the other another interesting thing which is coming here is the better GIL global interpreter lock, which I think Juliet mentioned a few minutes back. It's very eager. The Java embedded Python instance releases the GIL lock pretty eagerly as opposed to other Python implementations. That's one of the reasons why we are thinking of embedding the Java embedded Python within the JVM process to speed up scoring. There are other interesting integrations which come out of the box. There's nothing more we had to do as a part of the framework, because, for example, if you take some of us might be familiar with H2Os, wherein you can use the H2O Exadata framework to develop your models, and that framework allows you to export, just like Python allows you to export a model as serialized version, or R's allow you to do that. H2O also has got a mechanism to export your model which you have built using H2O framework, and this model comes on two versions, the Mojo and the Pojo. They call it their version of model export. This comes out of the box support from Apex, because all it does is it basically knows how to serialize and deserialize within the operator. There's nothing fancy that's being done. It can be done as a basic implementation in Apex. So we have seen three programming language constructs transformed into a streaming engine, in the sense that what we have done is the data scientists are not being forced to change their choice of language. They're still coding in their own resources they have, and we are taking that output, which is the model scoring component, pushing it into the JVM, and then intermixing it with a low latency streaming engine, which will deal with feature engineering, scalability, resource management, and a whole lot of other things, and embed both of these as one unified framework. And this allows us to do a whole lot of different things. For example, yesterday Bob was mentioning about canary deployment at the dark channel. I think what was the term used. You can do some of these deployments, because what I can do is implement a stream codec which takes the tuples of a certain section of the streams to go into only this new version of the operator, and rest of the traffic goes into the production version. So you can actually stream your subset of your population into, for example, the first 2 instances of the model scoring, and rest of it can go into the thing which was the current production model version. You can also do things like dormant models. This is very interesting because you can actually score. You'll see here you have taken the input from Kafka, Cassandra enriched model scoring, which is the lower scoring, and is going back into a TCP socket, which is returning to the channel which made the call. But you can also do a dormant model, which is up, which means that you're still doing 2 scorings. Only one is being used to return a response to the end channel, but the other is still being scored and being put into store. Interesting thing is, people might question there's data collisions, but you can, the Cassandra operator which comes out of Apex, you can do interesting things like non-collision data modeling out of the box by just prepending or prefixing your column name with something which is specific to the canary model there. You can also do other interesting patterns where, like, you have an ensemble model kind of pattern wherein there's multiple operators which are part of your pipeline in terms of scoring, and you can build one operator which takes the input of multiple scores done in parallel and apply a basic ensemble approach to it, and then give the score as the response to the channel at the end of the day. That kind of patterns is also possible. This is another interesting thing, I think, which I believe is a bit different than other streaming engines, is a command line client interface. For example, you have a certain threshold parameter which you deployed as part of the application deployment, right? And then you can use that, you can change the deployment or the threshold parameter at runtime without getting the application down. For example, if the value of a boundary or threshold is 4 and you want to change it to 5, that can be done by just using the application client, command line client. You launch your client and say, I'm connecting to this application. The application is still running. After you connect to the application, you say, I want to change this property of that operator. That can be done. You can also change the logical model of a DAG, and that means if we are to say that application came with a default set of say for example tracing operator, which traces the performance of an operator thing. You can inject a new operator into the DAG without getting the application down. That means you can trace the performance of your application perhaps in a few minutes of a day by just launching your command line client, alter the DAG, and then let it capture some metrics, alter the DAG again, and come out, and your application is still running this streaming engine as is without getting it down. The last use case I want to touch base is the customization power of Apex, right? So what we have seen is this set of operators, and someone asked, how can I make sure I can version this? I know versioning is a deeper subject. I agree with what Jill mentioned, but there's also use cases, for example, when you have a dormant operator model or canary model which are okay to experiment with, and you would like to not change a lot of things, but you still need to version it and get it out. You can extend, for example, any of these operators. In this case, we are extending the Python operator and give it a Git version aware Python operator. That means you have the basic Python operator, you're taking that operator which came out of Apex or basic default implementation, you wrapped it around with a construct of Git awareness, in the sense that because all our models are serialized, if a data scientist were to work in his own world and then commit his model by checking into Git, you want this Git version to be polled every, say for example, every 20 minutes or whatever, and then you want to get it out and use that as a model for from the next window. Those kind of patterns can be implemented. This is just an example to say that customizability and extensibility is something which is given by Apex in a really good way. Not that this comes out of the box. You can do is what is being done right Here are some production references. GE used Apex, and they basically claim sub-millisecond. This is the content I took from one of the marketing references. So I can't claim, but what I can definitely claim is I was previous to CBI, I was part of a company called ThreatMetrics, and we were doing 200 node Cassandra cluster kind of traffic at 240 countries kind of thing. And Apex really did well for the fraud visualization pipelines, data ETL pipelines to a very good extent. It was pretty low latency. It was a single-digit millisecond, which I can vouch for. And I think there are some other use cases in the community which talk about Apex's power to connect to multiple sources and things like Teradata's and Vertica's and Hadoop's and S3 file systems, which refers to the lower time to market value kind of offerings. That's all I have for today. Any questions?